of Java, which was then a colony of the Netherlands. And I'm just curious, how many people have been to the Netherlands? Anyone? Yeah, okay. And has anyone been to Java or to Indonesia? Oh, good, I can provide lots of misinformation and no one will know. Okay. So, the year is 1886. It's October. Eichmann embarks with 2 other doctors from the Netherlands, there, travels down through the Suez Canal, which has only been open for just a few years, and arrives several weeks later at the island of Java in Indonesia. So, Java is part of a large trading network involving the Dutch economy. And being there is a new experience for someone who lives in the Netherlands. You guys can just look out the window and start enjoying the tropics. But for those of us who live in temperate zones, it's just a wonderful revelation. So what do we see? Huge trees with large roots that go towering into the sky. And this is like, we just don't get trees quite that large. It's amazing. And the jungle is filled with rattan vines, which are harvested by the natives and used to create tatami mats in Japan. In other places, there's growing lots of crops, sugarcane, coffee, things which you might be familiar with. And many of these places have, they've taken down the forests, cleared the land so that they can actually build these things. This is an important part of what it means for this to be a Dutch colony. These are cash crops. These make a lot of money for the Dutch. Okay. So this is life on Java. This is the small little enclave of Batavia. And so they have created a little bit of the Netherlands inside the island of Java, much, I think, the same way that the Portuguese made little enclaves in Salvador and here in Sao Paulo that were just sort of like not like the surrounding areas. But they still have to deal with the tropical heat, which they're not accustomed to. They also have to deal with different kinds of diet, and in particular, rice, which is native to this region, but not necessarily to the Dutch. And disease, cholera, influenza, plague, dysentery. So one of the other diseases there is beriberi. Whoops. We'll go one more. Beriberi is, in fact, the reason why these doctors have come to Java, because while this has been endemic to the area, suddenly there has been this large rise in the incidence of this disease. How many people have heard of beriberi? How many people actually remember what it's about? Yeah, that's how it is sometimes. So let's tell you a little bit about the disease so you can become familiar with it. In the native language, beri means weak. And if you want to intensify the meaning of something, you double the word. So beriberi means weak, or very weak. So people suffer from fatigue. They lose sensation in their extremities. Sometimes they become confused, dazed, and, actually this, they lose muscle control, particularly in their extremities. And in some cases, now we can go here, fluid accumulates in the legs, in the limbs. Yeah. So we get this fluid accumulation, which taxes the heart, and so people can actually die of a heart attack from having this other case. So these epidemics were spreading. Anywhere from 1% to 80% of the patients died. So this was beginning to interfere with the trade. The fleet crews that would load the ships were no longer able to do that. That's interfering with the Dutch economy. The Dutch government wants that fixed. But even worse, some of the Dutch sailors and the Dutch military were coming down with this disease, such that there was a revolt somewhere inland, and they couldn't send the soldiers in because the soldiers weren't feeling well. So there we have a reason for sending these doctors to Java. Okay. Eichmann and the other doctors are not the first to have dealt with this disease. It's been known for hundreds of years in China. But no one really has a cure at this point. But this is what the Dutch want to try to do. Now, I want you to imagine for yourself that you have your medical degree and you have a little bit of experience in research, and you come up with a strange new disease. Imagine that. Strange new disease just coming out of nowhere. How do you figure out what causes it? Well, you just know, or you hope you know, or you have to sort of like go around. So let us take a sample starting off with, what do we already know about the kinds of things that do cause disease that might be applicable here? Okay? And we don't even need to have discussion for this. We can just go around and I'll bet you everybody can come up with a separate cause. So we'll start. A cause of disease. Insects. Deficiency. Okay. Air? Anything about the air? Just breathing air? Bad air. Mal air? Pollution. So we all know about malaria, yes? Mal air, it's bad air. Bacteria. Worms. I'm just going to make that a category that says parasites. Not just worms, but all kinds of icky things that get in our body. Marcos. Yes. Oh, autoimmune. And we might say they are both forms of pollution, but if we're studying the cause of the disease, where the pollution comes from might actually matter. So we can call those two different things. Sanitation problems. How many of you work at a board, at a whiteboard or a chalkboard? Every day. Okay, for those of you who don't do this on a regular basis, you would be surprised at how difficult it is. You just get totally disoriented. So you write sign it. Oh, wait a minute, where was I? How do you spell this? Okay, yeah. Animals. So can you get, that's a really general category. Can you give me an example? What's the example like you're thinking of? Insects? Okay. And worms. Fluids? Is that different than water pollution?
Like saliva.
Ah. Um, um, viruses. Are we thinking of any particular virus? Okay, and what is an infection? It's a form of a bacterial infection, right? So, good? Poisons, of course. Chemicals. Malnutrition. Not just vitamins. Oh, genetic causes, of course. Funguses, fungi. Poor hygiene. Yeah. Work. Heavy work. This causes a disease. We'll call that exhaustion. Okay. Anyone want to mention voodoo? What? Curses. Yeah, why not? Okay. So, this is a very broad range, and you can't just tell by looking at the disease which it's going to be, right? You have to start looking for clues and signals and things. But this is the challenge every time something like COVID comes up, or before it, SARS, or any of the other emerging diseases, monkeypox, or et cetera. You have to look for clues that might give you an initial indication like, well, we don't see any particular sign of a surface infection, so it probably isn't that, but they might have some bacterial disease for some other reason. Okay, let's add a little bit more of historical context to this particular episode. The role of genes, not really even sorted out yet. I mean, this is where we are. Uh, viruses, not known for another 30 years. Bacteria, well, now, this is interesting because germ theory that says that there are microorganisms that cause disease is new, and that we'll come into that. Autoimmune, completely unknown. Vitamin deficiencies, well, what did you, a deficiency of what? I don't know what you said. A vitamin? I don't know what that is. So you can see that their list was substantially smaller. But this was their challenge. So I mentioned that we were in 1886, and and that plays a role in where we are at this point. So Eichmann's own history gives us a little bit of background into what's going on now, because he had been to Java before. His medical education had been paid for by the Navy, and so he was sent out to serve in Java for a couple of years. And after having been there for a while, he contracted malaria, one of those other tropical diseases, and as a result, he had to be sent home. After he came back, he became interested in this new theory we just mentioned, germ theory, that diseases could be caused by microorganisms. Wow, that was like breathtaking, groundbreaking. And so he switched from being a practicing doctor to pursuing medical research. And he went to study with the leader in the field, Robert Koch, and then the other leader, Louis Pasteur, in France. And while he was there learning about germ theory, he met these other two doctors who had been sent there to learn the techniques of germ theory, to be able to take this knowledge, which was still very new, and it isn't like in any textbooks, it isn't in journals that you just go onto the internet, and believe me, you were not just going to Google any of this, because there not only was there no Google, there was no internet on which, and all the journals that would be there weren't there as well. So what was so special about the knowledge that they had? Robert Koch had developed a method of culturing bacteria, not just in meat broths, but on solid medium. So he could spread out the bacteria, and each individual type of bacterium or species could then grow its own colony. He could isolate those and test them individually. And using that technique, he had determined the microbe that caused tuberculosis, and then cholera, and then diphtheria. So this was like the wave of the future. This is how we're going to solve our diseases, by using these new methods to isolate the bacteria, transmit them to other organisms to show that they are effective in causing the disease, and then extracting the bacteria again from the diseased organism. This was how germ theory was making all these landmark discoveries. Okay, let's move on. So Eichmann and his team work for a year. They are diagnosing patients. They are doing tissue studies, so they're looking at things under the microscope, and they confirm that there is degeneration of the peripheral nerves. So the nerves are actually beginning to die. And they've been trying to collect samples and inject them into animals and get them to take the disease, but they're not being very successful at this point. But they conclude their report saying, because this beriberi is found in prisons, on ships, insane asylums, and other institutional settings, it has to be, they figure it has to be contagious somehow. But what's interesting, they figure, is that it doesn't seem to be immediately contagious. That someone moves into the area with, and they don't get beriberi immediately, it takes a couple weeks or something. So they think, well, maybe we have landed on a new way, a new kind of bacterium that doesn't just cause the disease, it has to be accumulated over several exposures before you actually get the disease. Well, they write this all up in their report. The government money runs out. That's what happens with research funding, right? Eichmann's colleagues go home, but Eichmann is familiar with here, so he stays on, starts working in the medical school as a teacher, and continues his researches on beriberi. So he continues along for quite a while. And he's continuing to do all the standard methods of trying to inject the animals and extracting things and trying to isolate the bacterium, still proving unsuccessful. Well, now the things get more difficult because he just needs to have more samples and more things. So he starts switching from studying rabbits to studying chickens because they're cheaper, easier to keep, and apparently they can show signs of the disease. Well, he goes along for the while and is trying to do all these injections when suddenly all the chickens get sick. He tries to isolate them, tries to put them in different locations, figuring that one has infected all the others because they were in the same thing, and he can't, they still stay sick. And then he starts isolating them again, and all the chickens get better. All of them. Now, if you had a result like this, what would you do?
Sit and cry.
Sit and cry. A very, very effective research technique, I think. And to prove how effective it is, let's just sample how many people have done scientific research and have had this experience of just sitting and crying over the results that you've received. Okay, so this is part of the nature of science. But it's not on the consensus list, and it needs to be. So this is a challenge for you now. I want you to get together in groups of 2 or 3, whoever is nearby, and figure out what you can do at this point, given that you're just a mess, and you decide to call over your best friend or another researcher and says, I just don't know what to do. What do you think? And you can just start brainstorming ideas. Okay? So take a few moments to see how you're going to pull yourself out of this miserable situation. Because they just they serve it, and then they throw out the leftovers, and I thought we could save a lot of money by using it. So that's what I was feeding the chickens until a couple of weeks ago when we got a new chef. And the chef said that he wasn't going to let civilian chickens have military rice. So I had to go back and switch to the native raw rice. And so that's what I've been feeding them. So I don't know. I just thought you should know. So let's show the next one. One more. Yeah. So there was this is the regular rice that normally gets served, and it's not brown rice, it's red rice, because we're in Indonesia, in Java. But for the military, they take the coating, the pericarp off of it, and you get white rice. And it was, in this case, it had also been cooked. So it had already been served. So we have this major difference. Now, with this information, just a casual comment from your assistant, now what will you do? I interrupted you just so you could get the sense of like, wait, what? I'm thinking here. Why are you doing this? But now you have this information. Can you use this, do you think? Yes, maybe? At least it changes the way what you're going to do, right? So go back to your group and see what you want to do now that you have a little bit more information that has arrived on your doorstep by chance. Okay.
If the problem is eating one of them or not eating the other one.
So essentially, if they don't eat something, then they're avoiding some kind of a poison or a toxin or a microbe or whatever that would have been in that particular rice. As opposed to if they ate it, then so you had to check both. I think that's like a 2x2 matrix thing. That's ANOVA value. I mean, we don't have statistics at this point, but we'll do it in an ANOVA analysis anyway. Okay. Anything else? Yeah. I think you said another thing, but I forgot what. Production. So in this case, that might have to do with what happened at the mill, presumably, because you're not producing rice, you're processing it or what. But yeah, same general idea. Anything else? There are lots of alternatives. Science is very open-ended, isn't it?
So there are other conditions that could be replicated or should be replicated for the test to make sense, like storage. So how long the rice was kept after being cooked, that sort of things. Yeah. Yeah, for the test to be compared to the last test, the conditions must be the same. Or
So you can't just try something, you have to try it under the appropriate conditions of comparison. So yeah, controlled experiments. Did someone teach you about science along the way? Some science teacher? Anything else we want to add at this point? Yeah?
We basically discussed the ideas of testing the rice, like I think it is expressed in the whiteboard. But we also were thinking that it might not be the rice. What is the credibility of the claim that the rice is the question? And we are all focusing only on the rice. We can find evidence, but that can be correlated with other reasons, and we will think it is causational, and it is not. So we shouldn't stop at looking only at the rice. That's the point.
Okay. This is a really nice list. Everyone agree? And this is how science happens. It's not like we'll just develop a hypothesis, we'll develop a test and then confirm it or deconfirm it, and we're done, right? This is much more how science happens. It's really can get kind of messy. Okay. So, what did Eichmann do? I'm sure you're interested to know. So they did start just using the rice diet informally, and if they gave them just, whoops. If they gave the chickens just the white diet, they would get sick after too long. And then if they gave them the red rice, they would get better. They'd be lounging around, lying on their side, which you may know chickens really don't ever do. But within a couple hours, they would be up, moving about again. It was like this magic cure. So they really started to focus more clearly on the rice and what was going on. And fortunately, we have Eichmann's lab notebook, so we know what he did in some level of detail. And the first thing that he did was to look into the cooking of the rice, as you've suggested. Was it spoiled overnight? Was it simply that the rice sat for a while and some bacterium got in the rice and then infected the chickens? Well, he ruled that out. Was it the cooking of the rice? And it was like, no, so he could feed the raw rice as well. Was it contamination in the water that went into the rice? He tried that. No, nothing of that sort. And then he finally said, was it the hospital rice itself? And he went, yes. So, Eichmann now had in his mind an important clue. He's been looking for the bacterium, right? Where do you suppose the bacterium is located at this point? According to Eichmann, it has somehow gotten into the white rice. But he knows that by feeding them the red rice, they get better. So he figures there must be some kind of antitoxin in the coating that's going along. But he tries to make these cross injections from the chickens that do get sick, and he still can't transfer the disease from one chicken to another. So he has to back up, and he reasons, okay, so the bacterium isn't actually getting inside the body. It's in the rice, but in the gut, it must be producing some kind of a neurotoxin that gets into the body, and that the antitoxin is working against it. Eichmann starts trying to publish some of these results, but not everyone who reads about these results is convinced about Eichmann's conclusions. Now I'm wondering, just without me having said anything more, how many of you are thinking like there are other hypotheses and alternative explanations that are available here? You're already starting there. So let me give you some time to think about what could these other people be thinking as an alternative explanation, and if you were Eichmann and wanted to respond to that criticism, what experiment would you pursue to differentiate between these two alternative explanations? Is that clear? Is this good? Are you having to work? Good. Okay, let's get back in the groups and talk some more. And the toxin of various sorts along the way. Meanwhile, research on germ theory around the world is advancing. A Japanese researcher and a French researcher have each independently isolated the bacterium associated with bubonic plague. Cholera vaccines have been distributed in India to 45,000 people, and the incidence of cholera is reduced by about 70% in those who receive the vaccine. Meanwhile, there's a critic in Germany who thinks all this is utter nonsense, and to prove it, he swallows a test tube of live cholera bacteria on the assumption that he's not going to get sick. And in fact, he doesn't get sick. Eichmann eventually goes back, and one of there are several criticisms that have come to him. One is like, he's done such a small sample, it really isn't very effective. And he's been studying things in chickens, and who cares about chickens? Why keep on studying this disease unless you know this is what's happening in the humans? And this is a general problem we have with model organisms. Do we know that they are actually representing human diseases? So Eichmann decides to try the whole diet thing with human populations. Well, and you can imagine, I hope, the dilemma. Are you going to like take a population, separate them into two, and feed one group the red rice and the other group the white rice, just like you do with the chickens, because it's a controlled experiment, and therefore expose these people to presumably disease? How many think that's a good idea? Well, back then, it wasn't such an absurd idea, and several years later, there was an American pair of doctors that took a workforce into the jungle and did exactly that. But they were fair about it in a sense, because after one group started getting the disease, they figured they knew what the cure was, so they switched the groups. So the ones that had had the healthy diet were then fed the white rice and vice versa, and then the other group got sick. So it was fair across the board. Nevertheless, Eichmann decided that if there was already an incident of beriberi, it would be appropriate at least to try a diet of the red rice if they had been fed just the white rice. And he found a prison in Toulon where there was like a 5.8% incidence of beriberi, and he convinced the staff to feed them the red rice, and indeed they all got better. Is that proof? Seems like it's cause and effect, but there could be all kinds of other correlated factors and confounders, so you don't really know because you haven't done two groups side by side. What could he do? Eichmann went to the head of the public health service in Java, who had access to all the prisons all over Java. 100 prisons, 280,000 prisoners. And in each prison, they were either fed a diet of white rice or red rice or a mixture of both. There you are. So we're going to look at the results that Vorderman produced from this study. Can you read that? It's not very large. It's okay? Okay. So polished rice is the white rice, and you can see that the percentage of prisons with beriberi, this is just, in a sense, he didn't have to set up this experiment. It was already in process. So this is what we refer to as a natural experiment, one where the conditions are already there, but they provide this comparison, this parallel comparison that we're looking for. So 70%, so 1 in 39 getting the disease. And whoops. And where it was half polished, the incidence was only 2.7, so 1 in 10,000 prisoners. And where it was mixed, it was intermediate. So you probably want, well, what are the p-values, for goodness sake? But we're in an era where they haven't refined statistics at that level. They're just beginning to start doing that. But in a sense, we don't need much statistics to realize this is a pretty dramatic effect size, and we don't need to fuss about whether or not it's marginal or not. Okay. First question now for you to go back and think about is, they also collected this data about the age of the buildings, the floors, whether they were permeable or not, the ventilation, whether it was good or faulty, and the population density, and looked at the incidence, and as you can see, there's really no correlation on any of those variables. But why? Why even bother? If you have this, why collect this information? Take a few minutes just to sort of sort that out, okay? through the rice, or did it arrive through some other means? So they had to rule out that it wasn't just how close all the prisoners were to each other and how dense the population was. It didn't come through the air. It didn't come up in the water in the floors. And it wasn't sort of like just leaking out of the buildings from the age. This was a pretty significant study and convinced a lot of people, at least at the level of like, well, at least if we just get the rice thing sorted out, we'll be doing well. And a lot of institutions changed their diets as a result. Let's just take a moment, though, while we're here, to pause about this very significant experiment and what made it possible. When I told you there were 100 prisons and 280,000 prisoners, were you impressed by the sample size? Yeah? How many of you thought about where those prisoners came from? Anyone? So this was, in a sense, a reflection of the colonial presence and the resistance to the Dutch being there, that all these people were in prison. And ironically, that's what made the large sample size possible. And it tells us a lot of things, that they didn't do a lot of investigation of like probing the native people about how they treated this disease. They might have found out something. Nor did they involve the native population in the investigation or simply say, this is your problem here in the thing. Let us give you the resources to help you do the science yourself. So in an ironic way, a very important discovery was made, but enabled, in a sense, by the colonial presence. Okay, we're going to kind of jump ahead a little bit, because Eichmann is now basically satisfied that he has done some important work, and he gets malaria again. And he goes back to the Netherlands and is basically says, I guess I'm done in Java. He does a little more work on the curative factor, so he takes the rice cuticles, the pericarp, and he sees if he can dissolve the curative factor in water. He can. He tries to dissolve it in alcohol. Dissolves in alcohol. He heats it to varying degrees and finds out that it becomes destroyed at 120 degrees, publishes this, and then stops his research. However, his successor at the hospital in Java continues the research. So how many do we need to go? Oh. Yeah, that's my... Oh, the prisoners that weren't executed, that is. So this is Gerrit Grins. Gerrit Grins comes into the situation, and I don't know if you said that there were alternative hypotheses and you were wondering why we haven't addressed them all. Gerrit Grins is going, why do we think there's something in the white rice? We have no proof of that. Maybe it's something in the red rice that's important, and if you deprive them of it, people get sick. So it's rather than something causing the disease, it's a deficiency of something that's causing the disease. Maybe there's some nutrient in there. And here would be a very good occasion for you to say, okay, for me to say, what kinds of experiments would you do as Grins to test that hypothesis? Well, we're just going to move on and look at what he did do. He looked for other ways in which that this curative factor might be found, not just in the red rice. And in particular, he found it true in mung beans, cacho ingo in the local lingo. And, yes, he tried other diets besides just rice, most of them based on starch, tapioca, or manioc, just pure stuff, or taro root, and found that they would create the disease as well. So he began to show in a number of ways that things did not line up the way Eichmann had said that they had done that implicated a bacterium. Okay, we're going to kind of rocket ahead to the end of the story so we can have a nice reflection on one of the puzzles of this particular episode. Several years later, Gowan Hopkins is working in England, and he's working on diet. And he finds that these mice, he gives them everything we know they need. They need protein, they need fats, they need carbohydrates, and they need water. And he gives them all purified forms of these, but the rats still get sick. Until he gives them like a milliliter of milk a day. And all the mice are okay. So Hopkins begins to start thinking in terms of nutrients that are not big nutrients like we're accustomed to, but what he calls accessory factors, or what we might think of as micronutrients. Okay, let's go on. That intersects with work that's done by other people. Casimir Funk, who is a Pole working in London, and Umatari Suzuki working in Japan, and they both isolate a particular chemical that is this curative factor. Funk does the analysis and decides that they all have nitrogen in them, and that somehow this must be significant for making them an accessory factor. He calls them, I don't know, vital amines, or for short, vitamins. So, I mean, we entertained the idea of vitamin deficiency, but that never would have occurred to the original group because there was no such concept of vitamins at the time. This is how vitamins were, in fact, discovered. And eventually, Hopkins and Eichmann, who was much more aged at that point, received the Nobel Prize in 1928 for their discoveries. Okay? And here's the wonderfully amazing, ironic thing. Did Eichmann get the right answer? No. And in fact, when Casimir Funk published the idea of vitamins as the cause of beriberi, Eichmann sort of scoffed at it and said, like, no, that can't possibly be the case. He eventually accepted it several years later, but we have all these controlled experiments that were done along the way with the chickens and with the humans that all were coincident with Eichmann's way of thinking about it. And yet he was wrong. How are we to reconcile this? We always like to parade this idea that science is tentative, science is provisional. But this is, if scientists make the errors, this is a really significant factor, at least in public trust in science, like, but scientists can be wrong. So if we want to address this, we really have to understand and help people understand how scientists can be wrong, when they can be wrong, and what that implies for us as non-scientists in judging their claims. So I want you to spend just about 3 or 4 minutes in your small groups talking about this notion of controlled experiment. How can you have conduct your controlled experiment and be wrong, which is what, every single school teacher textbook kind of model tells us. You do the controlled experiment, you make the conclusion, you publish it, and that's science, we're done, right? So how are we to understand this, and how will this help us then interpret other scientific claims that are made in public today? Okay? Interesting question, but we'll just spend a little bit of time seeing how far we can get into it, okay? Eichmann got the Nobel Prize along with Hopkins. The beriberi vitamin was not just isolated, it was identified. It is thiamine, as you may know. It's an important component in CoA, which is part of acetyl-CoA, which is part of getting from the electron transport, from the Krebs cycle to the electron transport thing. All you biologists know that, but it's always good to be reminded, like, oh, yeah. And since it's involved in energy processing, and since nerve cells use energy at a much higher rate than other cells in the body, all the visible symptoms of beriberi basically fall out from that knowledge. But it does pose this interesting question about what was the nature of the discovery and who discovered vitamins? When were vitamins discovered? It's a very simple question to ask, and you're supposed to be able to say, well, it was so-and-so in such and such a year, because that's what we're accustomed to doing. But you know enough of the history now to know that, like, you need to unask the question. So we're going to end on a slightly philosophical note. For you, we're not going to have time for the discussion, but you can take this with you and let you think about it. The doctors were sent off to Java to find the cause of beriberi. What was the cause of beriberi in Java in the 1880s and 90s? Was it a vitamin deficiency? Or was it a white rice diet? Or was it the economic conditions that led to a poor diet? Or was it the introduction of steam mills by the Dutch and the French and the other colonial powers all across Southeast Asia that led to the white rice? Or was it the whole system of colonialism that established those conditions? Each of those causes, biochemical, dietary, social, and cultural, imply a different cause in a different way to solve the solution of the disease, if you think about it. And that might be another intriguing nature of science question to pursue. What do we mean by causality? Is it a simple A causes B kind of thing, or are there much more complex contexts for us to think about? Yeah, that's a good one. Wow. And I could get involved in that even as a teacher. Okay, so that's the story of Christian Eichmann and the cause of beriberi. I hope you found it informative. I hope you found it another example of using a historical case and using inquiry things along the way. The version which you can download has more questions that you can choose to insert depending on which class you're using and how much time you have and what you want to get across with your class. But in this case, I want to underscore that this is a lesson, again, about the nature of science and particularly about the nature of error in science, because it's certainly my conviction that if we want citizens and consumers to understand about information, scientific claims, misinformation, false claims, the reliability and credibility of those claims, one of the things we have to do is unpack what we have always been saying, that science is tentative. How do errors occur? What are the limits of our scientific knowledge? Where does it end? Where do things remain uncertain? And is uncertainty a status that we can assign to science and still believe in science? So I hope that has all helped along the way. In closing, do we have any comments or questions about the case or its relevance for the focus of what we've been doing the last couple days? You've all learned that if you pose a question as a teacher, you have to allow students time to think. To write the question, you can't just like go ahead, right? So I've been trying to do that. Do you have a question, Maria Elice? Yes.
Do you have any data applying this case with students, real students in schools?
Sad to say, as much as you might think I'm an expert about science education, I have a lot of experience. I have a lot of background in history of science, a lot of background in philosophy of science, but I am not an educational researcher. But if you want to know how this works, you can talk to the many people who have tried this case on other occasions. And a lot of it is very context dependent, and it's the teacher just makes it work. It's wonderful. Okay. We want to shift gears now and look ahead to start compiling everything that we've learned and taking it forward into your professional practice. So, we don't have an exam. Yay! There's no final term paper. Yay! But we would like you to be able to try and consolidate what you've learned and put it into a practical context of what you are likely to use. So we want each of you to create a small lesson in science media literacy. And let's deal with the computer stuff. So, what we'd like you to do is to focus on one particular case, historical, possibly contemporary, but to be used with great care, or a particular concept, something we've already dealt with, or some elaboration, such as, you talked about expertise. Well, what about if experts disagree? That's a very specific concept. Or we've talked about bias, but a very important bias is conflict of interest. And create something specifically to help students understand more about specifically conflict of interest. So one case or one concept, keep it narrow, make it achievable. Okay? And then we just want you to think through this case. You don't actually have to write it out. You don't have to develop materials, no handouts, you don't have to test it in your students. This is a conceptual piece about taking what you've learned and thinking about how to teach it as well. So, describe your educational purpose or your learning objective. Not just the concept, but like, how do you want to see that realized in students? Perhaps in terms of specific competence that you can observe or test. Describe the activity, and in particular, how you're going to engage students in their own learning, as we have demonstrated here in this class. We're not just going to make lectures. We're not going to make templates and have them fill in the forms. We're going to have them think through the concepts and develop them on their own. So to do that, this is essentially your outline, but it's not a regular outline of statements. It's a question or problem outline or a sequence. Remember, we looked at the structure of the vaccine case, and we had a sequence of questions that led together. So it may not be a historical case, but there may be 1, 2, 3, maybe 4 questions in a row, and we should be able to talk about what those well-framed questions are, and in particular, ones that will lead to open-ended discussion that have good answers and poor answers, justified answers, and ill-considered answers, but not just one right answer. And that should be easy. If you haven't done it before, guaranteed, it takes a little bit of fun. Once you get in the habit, it's not difficult. But getting there to begin with, because you have to turn things inside out. So, this is like Jeopardy. You have the game Jeopardy? They give you the answer, and you have to pose it as a question. So, the answer students to be able to give you that as an answer. What is the question that you're asking? Anyone know this? What is the square root of 4b squared? To be or not to be. So that's the kind of way that you have to think inside out. So this is a short thing, 500 words, 1 page basically, right? And when you're done, please just run it through Google Translate. So we have a really good, it does not need to be published, but it would just be helpful if you do that as part of your thing, put it in the same document. And then we'll be able to look at it. And I'll be able to interpret it because I'm really interested to see what you have to come up with. Okay. Questions about the practice?
What's the deadline for submission?
What do you think an appropriate deadline would be given the circumstances? I can give you an outside deadline. But what do you think would be an appropriate deadline to set for yourself or that everyone should follow? 2 weeks. 2 weeks? Is that fair? So we will target 2 weeks, knowing that, oh, it's Friday, and no, I need another weekend to finish it up to make it the way I want it to be. At least you kind of like out there. This is not one of those things where we have to like give a PowerPoint presentation to the client on that day, and if we're not, we lose our job. There are cases like that. This is not one of those.
Any email to her,
Yeah, both of us, so we'll be together, yeah. And we will both be interested in seeing what you come up with. And you never know if you have a good idea. I might ask you to say, can you write this up and try it and publish it? Because this is really good stuff. This is a good group, by the way. And I expect to see cases with fuzzy. So we had a class of 3 dozen. In this very room, 9 years ago, we had another class of history and nature of science. And everybody had to create their own historical case study on the scale of the IB case study we just had. And these 2 guys, created a case. It's been published in a Brazilian journal, and next month it's going to come out in American Biology Teacher. The summary, it's online. You can download it by Carlos Scheinz. And there have been other Felipe Rousseau was in the class. It's going to be published in the same issue next week or next month. And there was another one on. You guys who are biologists, do you know about Brzezinski's relationship with USP? Yes. Really important evolutionary geneticist, and he was working here, so there's another case study based on that was published. And
Vital, there's the
Walls
Vital.
in the Amazon can be published, and Vital Brazil,
Vital Brazil.
that one's been published?
Not in English, only
Not in
in
English, but it's in Portuguese.
In
yeah.
Portuguese is published.
A really good one on Vital Brazil and development of snake venom. It's basically Nobel Prize quality work that didn't get a Nobel Prize. You guys know why. So yeah. We'll say great hopes without putting the burden of expectations. Okay. So clear about the parameters. Now the question is, and I'm trying to get you to think about this ahead of time. But we now have 18 minutes for you to get together with one other person or a couple other people. The more people you can hear, the better. The more feedback you get, but the slower it takes for her to get through everyone's ideas. So, what are we asking? No.
we will discuss this.
So if you have an idea, test it out with somebody next to you, see what they think about it. They might pose a question like, well, you're going to do this, you're going to do we talked about this, oh, yeah, I wasn't going to include that, but yeah, I should, yeah.
And this will be
This is going to be individual, yeah. You're all comfortable. Okay. So, this is your time now to start brainstorming on your ideas and getting some feedback from people who know something about the subject. Okay. So you can isolate the error, but then you have to convince all your peers because science is, after all, a collective enterprise. And in a strong claim, you might say, if it hasn't been endorsed by a majority of the scientists, a weak consensus, perhaps we ought not to call it scientific knowledge at all, at least not yet. It's an interesting thing to consider. So, persuading your peers. So, most of you know that Marshall and Warren got the Nobel Prize for the discovery that ulcers are caused by bacteria, not by excess acidity and diet. And they were able to convince their peers within a matter of a few years because they had done good clinical tests. But the idea had been around for decades, and it had never been corrected. What's interesting is that the idea about acidity and stress originated from understanding about hormones in the late 1930s. Antibiotics came out as a result of World War II, and some physicians decided that they were going to test these on whether or not they would be effective on ulcers. So as early as 1948, doctors were publishing results that antibiotics were effective treatment for ulcers, indicating, of course, that it was a bacterial cause. So from 1948 to 1985, all these people who had published these things were unable to convince their peers. So another way in which error needs to be followed through on. Yeah, okay, we'll come back to that one. Some of these are lapses in publication because something didn't get through peer review that should have. This is Lawrence Morley, who advanced a very important theory about continental drift. Avogadro is a more familiar case. He was a kind of there were the famous physicists that lived in the city, and then there was, chemists. Avogadro, who lived kind of like one of those rural cities, not very prestigious university, but he was able to resolve this problem that they were having about molecular weights and the volumes of gases. It's a really fundamental thing, but for it to be able to work on Avogadro's solution, you had to be able to have molecules that were made of two of the same kind of atoms. So O2, N2, H2. Well, that didn't fit very well with the theory of Berzelius, who had the electrochemical theory of combination, who really helped us understand the nature of ionic compounds. Powerful theory, powerful personality, dismissed Avogadro, along with John Dalton. And again, even if you're not a chemist, you remember the name of John Dalton and probably associated with atomism. And he said, but no two atoms of the same kind can connect with each other. That's just their very nature. So Avogadro's credibility was so low that even though he had a solution, nobody listened to it. And it took another 45 years until those big guns were out of the picture and somebody reintroduced the idea in a particular way, having like, oh no, Avogadro was onto something here. Let me just do one more thing and present it, and was able to convince people. So this is not such a rare event that we can't produce a long list of errors that were rejected by the consensus. You can go back and look at the list if you want to, but you can see that the number of years in which these errors persist can be quite impressive. So that's each step along the way. The other thing we might say is, if science is self-correcting, we might expect it to self-correct in a reasonable amount of time. How long, so it self-corrects, how long would you say, like, it's tentative before it becomes settled or durable? Interesting question, yeah? Because the way in which it is typically phrased is, oh, eventually, in time, ultimately, or in Shakespeare's things, at length, the truth will out. Well, here are some long-standing errors. We'll just put in a couple like humoral medicine, not 2 centuries, 2 millennia. Newton's speed of sound formula, 115 years. Particle theory of light, 140 years. Dinosaurs as exclusively cold-blooded goes back to mid-19th century, revised in the 1960s, 144 years. And our example of the Viceroy as a Batesian mimic, 122 years. So some of these errors can really hang around for a long time. And if we're not careful, anybody can say, yes, but what about Galileo? What about the Viceroy butterfly? What about Newton's speed of sound? You know, this could be a tool to completely disembowel the legitimacy of science if we didn't understand and explain how errors occur and how they are corrected. So here's one of my favorite examples of error correction taking a little bit of time. Did I do this in IHPST? Yes, I did, okay. So this is Mani Sigban, who got the Nobel Prize in 1924 for determining the wavelength of X-rays using X-ray diffraction, a bunch of equations. And then he gave the task to his graduate students, say, okay, confirm my results, but use a diffraction grating instead. Well, he got a different result, and it went through a long period of trying to like, well, what's wrong? Why is my result different? And he was so confident in his own result, eventually he tracked it down through all the calculations that his advisor had used and traced it back to Millikan's use of the value of the electric charge. Physicists can have a field day going back through this. Here it is. Millikan's number was incorrect because he had not used a correct value for the viscosity of air. A simple little physical constant that had not been determined with enough precision that cascaded through all these other things. Millikan's work on the electric charge, which received a Nobel Prize, without the error having been detected. Jean Perrin's value for Avogadro's number, for which he received a Nobel Prize, in which the error had gone undetected, and Sigban's determination of the wavelength of X-rays, for which he received a Nobel Prize, for which the error had gone undetected. So, how long does it take for errors to be corrected? 3 Nobel Prizes. In addition to errors being corrected, taking a long time to be corrected, sometimes they are corrected just by chance, by accident, or as historians we might say, by contingent events, in the same way that the chickens and the rice diet were so important in the Eichmann case. So Keith Runcorn was a geologist. He learned about paleomagnetism from his advisor, and he decided to do studies about looking at the history of the Earth's magnetic pole from looking at the magnetic field in fossilized rock. Can you figure that out? You find enough fossilized rock where it points to the North Pole, you get enough samples, they triangulate, they give you where the pole was at that particular time in history, and then you go sample some other rocks with a different date, and you end up connecting the dots and creating this curve about where the pole used to be. So this became a polar wandering curve. Well, Runcorn, being a good scientist, decided to go from the work that he did in Europe, he went over to America, and then he got a different polar wandering curve. And then he went over to Africa and got a different polar wandering curve. It's like, this is an incongruence. This is a discordance. Like, how can you have the same magnetic pole following 4 different routes all to the current where the pole is now? Much to his dismay, Keith Runcorn, who had always ridiculed Wegener's idea of continental drift, because that's what everybody else in the field did, had to admit that Wegener was right and that it was the continents that had moved, not the North Pole. So, and it took, I mean, he wasn't planning on discovering this, it just sort of creeped up on him. So here are another long list of examples of errors that were discovered just by happenstance. So if we think that there is a systematic way of rooting out error, we are fooling ourselves. We need to go back and be good historians and understand the role of contingency, not just in regular discovery, but in discovering errors as well. Error correction, as I think you can see from what I have been saying, requires work. You just don't spot it and say, oh, I was wrong, and now I fixed it. So when the Opera Collaborative announced that they had discovered a faster than light neutrino, it made international headlines. I remember reading it on the front page of the New York Times, and I go, whoa, well, let's wait and see. And indeed, they had to go back and check everything. They had to check every single cable, every single connection from one thing to another, and after 8 weeks of things, they found that there was a loose cable connection, here it is, close up, that meant that the time signal had been delayed, and if you're talking about faster than light, the velocity, well, velocity, again, even if we're not a physicist, distance and time, so time is like really critical. So the time signal was incorrect, but they were able to track it down. But it took like dozens of people a couple months to be able to track that down. Can go back and look at the example of Jon Snow later. So if we put all of that together, all those examples that we've just talked about, we begin to create a picture of what you have to do to be able to expose error in science. You have to keep on with the research. If you're not involved in active research, the likelihood of encountering the error just kind of drops off entirely, which means that it has to be funded. People have to be motivated because there's going to be professional credit for doing so. It has to be done in a timely manner, and it has to be not just trying to confirm it or replicate it, but to replicate it and probe it in a diagnostic way. And that's being discussed now in the reproducibility crisis literature. We need to have the social system of organized skepticism by which we examine each other's and vet each other's results functional, which means there cannot be credibility bias, which allows some people to have more say than others. We need open science, so that's a modern term, but they've gotten at this Mertonian idea, which has been around for over half a century, like we have to share everything. It has to be transparent. And you can't have a conflict of interest. And of course, this we already know from the misinformation stuff. We have to have enough background knowledge, we have to have enough technology, and we have to be able, sometimes these new hypotheses just don't occur to us because we needed somebody who had the right perspective, the right combination of ideas to say, but if this was this, then that would be true, wouldn't it? Let's look into that. And that sometimes requires a very particular individual. And we must have a diversity of perspectives so that there is no communal confirmation or cultural biases. So all those people who worked on intelligence were all men. And of course they had to conclude that women were inferior because they had smaller brains. Nobody questioned the fact that that benchmark might be an assumption that wasn't warranted because there weren't women in the field. Later in the century, once women came involved in the field, that was the first thing they went at, and the whole study of craniology dissolved in a couple years, simply by making a more diverse environment. So, yes, science is self-correcting, sometimes, or with qualifications. So I hope that this is an informative way to think about these are all aspects of the nature of science, and many of these things, although they are critical to the conduct of science and to the correction of science, we don't discuss in a science classroom. We talk about nature of science as though it were this simple thing between law and theory, between a very simple kind of method or two methods, and the difference between observation and inference, well, that's an easy thing. And when we've done all that, we think that they're going to understand how science works. So if we want people, citizens and consumers, to believe in science and to understand the credibility of scientific claims, and perhaps to be able to probe in a dialogue with scientists about how credible the claim is and whether or not the public should accept it as credible, they need to have a lot of background in the nature of science to know how the scientific conclusion was generated, to know where its strengths and where its weaknesses are, and thus how we should use that knowledge based on its levels of uncertainty. So this is my philosophical and historical research. The book is still waiting to be, at the press as to whether or not they're going to publish it. So I hope this has proved informative for you and will add depth to your understanding of the misinformation crisis. Okay? No, we're just there. Okay. So let's take a deep breath because we want to make a quick turn from this to thinking about everything that we have been doing for the past couple days. This is being kind of like a final little capstone to sort of say, oh, maybe, I don't know if this helps put things together or not. Okay. Let's take a moment to review. Here are some of the examples of misinformation and disinformation that are very much with us in our society and culture today. We're still dealing with the problem of convincing people about the reality of climate change, or that it's caused by humans, or that it's serious enough that we have to do something about it. Vaccinations, indirectly pandemics. Safety of nuclear power, still an issue. This is an image from La Foda about 8 or 9 years ago about whether the drought in Sao Paulo, the really bad drought about a decade ago, was caused by climate change and what it did to the air, to the water vapor over the Amazon and its relationship to moving. Do cell phones cause cancer? Well, of course they do, because 5G cell towers do. And everyone recognize this? Garrafada, yeah. A form of misinformation, yes? This is somebody profits from these remedies that are completely ineffective, and people believe that they are. So this is, in a sense, our challenge is to try and help inform people about how to address these issues. And we have now, at the beginning, I introduced what I took to be 10 basic or essential competencies that would be the foundation for being able to negotiate our way through all this mess. So here they are again. Basic epistemological beliefs about the nature of knowledge, saying uncertainty, that it's based on evidence and not just mere authority. An analytical posture, which means that people actually probe it. Epistemic dependence, the notion that there are experts and we all depend on each other for knowledge in a culture of specialized knowledge. That we can identify who those experts are. We can identify who the gatekeepers are that help to edit or curate the information that goes through the social networks, that we have some skills in detecting detection or in deceiving other people if we want, and in decoding some of the technology and social networks that contribute to that. That's all about the nature of media So science media literacy very definitely involves the media, but as consumers of the media, we are equally complicit. We are subject to confirmation bias. We need to understand that. We have all these other cognitive heuristic loopholes, the biases of social learning that we associated when we talked about the deceptive techniques and science liars. They're all using how our brains work to deceive us. And finally, understanding that through all that, the consensus among scientists, and sometimes a consensus among people who are trying to interpret science, is a really important element in being able to come to something that's trustworthy. And here, here's a reminder of all our activities. Introduction on global warming, Fantastic Beasts from the Renaissance, Vaccine Skeptics of 1721, Fast and Frugal, things about social networks, science liars, the New Madrid earthquake, plausibility, and do your own research, scientific institutions, the COVID conundrum, Eichmann, and things about self-correction. And if we map them out, you'll see that I hope we have covered most of those concepts by using a constellation of different activities. No one activity, this problem is too complex. You don't just have an afternoon where you talk about science media literacy. That's like trying to say, oh, I can teach nature or science in the first day of the class, and then they'll understand it for the rest of the year. No. You know that it has to be reinforced consistently over and over and over again. And in this case, it's because different kinds of things will highlight different kinds of activities. So I'm hoping that in another 2 weeks or so, we will have another list of 3 dozen lessons to add on to this list and fill in this little table that will give us more tools that other people can use to teach about science media literacy. So that's what I hope you can see as it fitting all together, but it's more important now, I think, for us to just sit back and say, okay, take a deep breath. What did I learn? And I'd like you to just take 2 minutes, personal silence, maybe writing stuff down, maybe just putting it on your fingertips, to say, yeah, I put in a lot of effort these 2 days. I gave up, sacrificed this and that to get here, and what am I taking away with me? What have I learned? So take a few moments to document and celebrate for yourself what you've learned. And then we'll take an opportunity to share it with others, okay?